We will not be going again into too much detail about this. You can just go to section 8 to the lecture notes or the relevant playlist. But it is important to point out that some of these scaling relations that we've seen are crucial, really, really crucial to understand galaxies. An important one is to understand the scaling of luminosity with temperature, meaning that the hot spectral types, essentially O and B class stars, are always going to dominate the luminosity, and the same thing for mass. So those hot spectral types are the very massive ones, and therefore they're very, very luminous. And also, this is crucial to understand the evolution of a galaxy, is the fact that if a star is very massive, it'll only live for a short amount of time, and therefore, as we pointed out already, spectral cold types and low mass types will accumulate as the galaxy forms more and more stars, while the hot stars that dominate luminosity while they're there, they actually do not. So if you see something like an O or B star, it means that the galaxy has formed stars relatively recently, and we'll come back to this as well. Now, say that we want to use some of our knowledge, and let's say that we take a spectrum of a galaxy and find it to resemble essentially the spectrum of an O-class stars. And on top of that, there might be some emission lines, because O-class stars will ionize the gas around it, which will actually recombine and then send emission lines like hydrogen H alpha or H beta. Let's say that we measure the distance to this galaxy by measuring a redshift, and we determine that the absolute magnitude of the galaxy, right, so this is not of the star, of the galaxy, is minus 21. Now, because we see that the spectrum of a galaxy resembles exactly the spectrum of an O-class star, it probably means that we're seeing just a sum of O star spectra that dominate the light, and that's why when we look at a galaxy as a whole, we're just seeing the light of O stars. Of course, this galaxy needs to have more than one O star, and that is because O stars are very bright, but their absolute magnitude is still something like minus 4. What this allows us to do, though, is to estimate how many O stars are likely to be in the galaxy given the total absolute magnitude that we see. In order to tackle a problem like this, what you need to do is have an idea of what is the absolute magnitude of that specific spectral type. You're given here in the problem. That would be minus 4. We're looking in the UV just to be specific. And based on the spectrum, we can make the assumption that essentially all the light that we're seeing in the UV is coming from O-class stars, and therefore we can very easily compare. If we compare the luminosity of the galaxy with the luminosity of a single O-class star in terms of absolute magnitudes, meaning 10 to the power of 0.4, and looking at the difference of absolute magnitudes, we would expect actually that to produce that absolute magnitude, you need something like 6 million O-class stars. One of the really important things that you need to know to understand galaxies is that if you take a spectrum of a galaxy and it looks like a particular spectral type, that implies that essentially that galaxy stopped forming stars for a sufficient amount of time to allow for all the other more massive, hotter spectral types to actually evolve away from the main sequence and almost certainly go supernova. So it also means that by looking at the spectrum of a galaxy, we can infer how old that galaxy is, at least in an average way. And thinking about galaxies as essentially linear combinations of stars, or more specifically of linear combinations of star clusters, then all the knowledge, all the things we've covered for stars will be applied to galaxies so that we can unveil, for example, the chemical elements that exist in a galaxy, or its current condition, or the age, how old a galaxy is, based on the stars that it contains. Because all of this, in case you have forgotten about the contents we've covered in section 8, this is a good time to recap them, specifically some of the properties of the different spectral classes, their colors, typical temperatures, and typical signatures, because interpreting a galaxy is really about looking at linear combinations of all these features. If you can actually pick up these features, then you can even tell how many stars there are of each spectral type. And if we use some very good modeling, we can actually infer, for example, the star formation history of the galaxy.